we're going to look at a whole bunch of stuff right now. So let's just start off with angles in standard form. So angles. An angle is formed with two rays. So I've got one here. I've got one here. All right. The angle between them is, we'll call it theta. The ray on the x-axis, so where I have that red line, that's called the initial side. The other one, the blue one, is called the terminal side. Think terminal as in end, so it ends on the terminal side. We measure, usually angles are in counterclockwise, so those would give us positive angles. And counterclockwise makes positive, and then clockwise would give us negative angle measures. Common unit for angle measures is degree, and 1 degree is equivalent to 1 out of 360 degrees of a full rotation. So let's try and sketch some. So if I look at like a kind of like a coordinate grid here, if I look at this as quadrant 1, 2, 3, and 4, we can kind of sketch where these angles could be. So 65 is between 0 and 90. So it's going to be somewhere here. And then we can just draw an arrow to show the direction. So I'm going from the x-axis counterclockwise to give me this 65. 320 is going to be in quadrant 4. Something like that. Start at the x-axis, go counterclockwise all the way to the terminal side. 415, it's bigger than 360, so it means we want a full rotation and then some. So the way we draw that is we start on the x-axis and kind of draw like a spiral, because we've gone all the way around and then some. The negative angles just tells the direction we are going. So it's almost like we start off at 0 and then negative 90, negative 180, negative 270. So negative 140 would be in the third quadrant. And we're going backwards. Negative 15. And then negative 210. Okay. Another unit is in radians. You got degrees, and then you have radians. So 1 full rotation in degrees is 360 degrees. 1 full rotation in radians is 2 pi. 180 is half a rotation. So in radians, that would just be pi radians. And then here's some formulas we can use to convert from degrees to radians and radians to degrees. So let's look at some. So degree to radian, we'll take the degree, multiply it by pi over 180. All right, so this first one we have 60 times pi over 180, and then we'll reduce the 60 over 180, which is just 1/3, so pi over 3. 60 times pi over 180, and then we'll reduce the 160 and 180 to give 8 pi over 9. 330 pi over 180, and we'll reduce that to 11 pi over 6. The negative angles, The formula does not change. We still use the same one. So negative 45 times pi over 180. And we still just reduce the fraction. So negative pi over 4. Negative 230. Whoops. Pi over 180 will give us negative 23 pi over 18. Negative 75 pi over 180. And then we'll reduce negative 5 pi over 12. Then we can go the opposite way. So radians, this time we'll have times 180 over pi. So times 180 over pi. Now the pi's are always going to cancel. And then we can reduce the fraction. So 180 divided by 18 is just 10. And then 5 times 10 is 50 degrees. The pi's are always going to cancel. 180 divided by 9 is 20. 20 times 11 is 220. Pi's are going to cancel. 180 divided by 3, I think, is 60. 60 times 7 is 420. Times 180 over pi. The pi's will cancel. And this leaves me with 30. Don't forget the negative sign. So negative 30 degrees. All right. Times 180 over pi. Let's see, the 180 and 12, I think can reduce if we do it by, I think it'll go in even. I'm going to divide it, 180 divided by 12, yeah, 15. So negative 19. Oh, I was going to say over, but it's just negative 19 times 15 to give 285. So negative 285 degrees. See, that'll cancel. I think this will give 45. And double check that. 180 divided by 4. Yeah, 45. And then 45 times 3 is 135. So negative 135 degrees. All right, coterminal angles. That just means they have the same terminal side. So we're going to see if these sets of angles are coterminal. So if I'm going from 305 down to negative 55, I'm going to take the 305. And if I'm going the negative direction, I'm going to subtract 360. We're either going to add 360 or subtract 360 is really what's going on. If I subtract it, I get negative 55, which is here. So yes, they are coterminal. 30 minus 360 is negative 330, which is not negative 170. So these are not coterminal. We can do it with radians as well. So pi over 4, we would subtract 2 pi, because that's the full rotation. But we're subtracting fractions, so really, wouldn't that be 8 pi over 4 to get the common denominator? So pi over 4 minus 8 pi over 4 would give me negative 7 pi over 4, which is not the negative 9, so no. Let's see, 3 pi over 2. I'm going to go ahead and subtract 4 pi over 2 to subtract that 2 pi, and I get negative pi over 2. And then I'm going to try again because I have a negative 5 here, and it might work. If I subtract another 4 pi over 2, so a second rotation, and that does give me the negative 5 pi over 2. So these are coterminal. All right, give two coterminal angles, one positive, one negative. That is as simple as taking 150, adding 360, and subtracting 360. So that would be 510 and negative 210. And we'll do one with the radian, so 7 pi over 6 plus 2 pi, which would be 12 pi over 6 to get common denominator. And 7 pi over 6 subtracting 12 pi over 6. So we get 19 pi over 6 and negative 5 pi over 6. All right. All right, we could have the degrees written as decimals or in a degree, minute, second form. Think like latitude, longitude. It's always that's how those are written. 1 degree is 60 minutes. 1 minute is 60 seconds. So 1 degree has 3,600 seconds. Some notation here. Degree, the symbol for degree is like a little circle. The minute notation is like an apostrophe. And then the second is like 2 of them. Think like if you're writing feet and inches, so like 4 foot, 8 inches. Same idea. All right, so to convert, let's go from degrees into the minute second. So we have the whole number is always going to be the degree number. So I really want to convert the decimal. So 0.875. I want to turn it to minutes. So I'm going to multiply that by 60 and I get 52.5. So I get 52 minutes. I still have a decimal, so I'm going to take that 0.5, turn it into seconds. I get 30. So 30 seconds. Let's try a couple more. So I have 15 as my whole number, so that's my degree. And then 0.48 times 60 gives me 28.8. So I get 28 minutes. Then I got to take that 0.8 and multiply that by 60. And I get 48. So 48 seconds. So this next one I have 150 degrees. And then 0.2 times, 60 gives me 12. And I don't have a decimal remainder there, so I can leave it like that. Let's look at one that maybe you'd have to potentially round. So I have 48 degrees, 0.526. I'm going to multiply that by 60. So 31.56. So 31. And I got to turn that 0.56 into seconds. So I get 33.6. Now there's not anything further for this, so I will just round it. That 6 tells me to round up, so I'll make that 34. Okay. So we could go the other way. If we were given it in that minute second notation, how could we get back to a decimal? So the 73 is the whole, and then this is out of 60, so 9 out of 60. It's going to give me 0.15, and then the 50 is out of 3,600 because there are 3,600 seconds in a degree. So we would do 50 divided by that 3,600. That gives me 0.0139. And then I just add these decimals together. So plus the 0.15 plus the 0.0139. So I get 73.1639 degrees. Okay. So I'll look at these odd numbers here. So I get 37 plus and 36 out of 60, which gives me 37.8. 6. This gives me 84 plus 52 divided by 60 plus 18 divided by 3600. So as long as I put parentheses around these, I can throw it in a calculator and I'll get 84.8717. So I get 310 plus 28 divided by 60 plus 20 divided by 3600. And again, put the parentheses and we'll get 310.4723. 50 plus 14 over 60 plus 56 over 3600. Parentheses around it, and it'll give us 50.2489. Right. Move on to something different. Go on to arc length. So we're trying to find this length here. So that formula is S equals R times theta, which is just the angle. And the angle is always in radians. So this first set gives us the angle and the radius. So I literally just plug it in and solve. So 3 times 5 pi over 6. And let's see, the 3 and the 6 reduces to just 1/2. So I'm left with 5 pi over 2. And then we want it in terms of pi, which is right here, and then to the nearest tenth. So I can throw that in a calculator and do 5 times 3.14 divided by 2 and get 7.9. All right, let's do another one. Let's see. S equals R theta. The only thing I'm going to do here is change that 0.5 to a fraction. So I can multiply those fractions. So I get 3 over 4 pi. And if I plug that in a calculator, I get 2.4. Right. There's some that are given in degrees, but remember the angle has to be in radians, so 15 times pi over 180. So S equals 8.4 times the 15 pi over 180. Let's see, the 15 pi can reduce to pi over 12. 8.4, let's see, that's 8 4/10, so 84 tenths, which can reduce to, if I divide 84 by 2, what is that, 42, 42? And then the 42 and 12 can reduce by 6, so 2 and 7, so I get 7 pi over 10, and if I throw that in the calculator, I get 2.2. Let's get another one. 135. I have to turn that into radians. Let's see, what can I reduce that to? 3 pi over 4. So then S equals the radius times 3 pi over 4 to give 75 pi over 4. And if I plug that in a calculator, I get 58.9. All right, let's see if we weren't given some information we had to solve. So I'm going to write the formula, R theta. Oh my gosh, I cannot draw theta, save my life. Okay. Central angle theta in a circle with radius 6 has an intercepted arc of 10. We want to solve for theta in radians and degrees. So I can just divide both sides by 6. Theta is, let's see, 5/3. So 5/3 radians. Let's turn it into degrees. So 5/3 times 180 over pi. Let's see, the 3 and 180 will cancel out to be 60. So what is that? That's 310 divided by pi, which is going to give me about 95.5 degrees. All right. We can also find the area of the section. So we can find the arc length, and now we can find the area. So the area is 1/2 theta r squared. Okay, my thetas are just going to be a 0 with a slash. And theta is still in radians. So I'm going to convert that 74 into radians. And I get, I could probably reduce that in half. 74 divided by 2, 37. So 37 pi over 90. The area is 1/2 theta, so 37 pi over 90 times r squared, so 4 squared. 4 squared is 16. 16 divided by 2 is 8. So I get 8 times, oops, forgot my 7. 37 pi over 90. It doesn't say what to put it in, so let's just multiply it out and get a decimal. So 8 times 37 times pi divided by 90 will give me 10.3. If we're talking units, it's area, so centimeters squared. Let's do this one. Area is 1/2 theta in radians. We're already in radians. Times r squared. These 2's will cancel out. So I'm left with pi over 3 times 49. So 49 pi over 3, which as a decimal will be 51.3. Units is in kilometers, so kilometers squared. All right, let's do a word problem or two. Area of a sector that has an angle 240 is 134 feet squared. Find the radius. Let's turn that 240 into, oh my gosh, I have the formula backwards all the time. Okay, turn it into radians. So it's pi over 180. Let's reduce that. Let's see, we can at least do it by 10 because they both have a 0. And I think we could actually do it by 60. So 4 and 3. So 4 pi over 3. So the area is 1/2 theta r squared. I want to find r squared, so that means I know everything else. So 134 is the area. 1/2 theta is 4 pi over 3 r squared. My 4 and my 2 will cancel out to leave me with just 2. I'm gonna erase this so I have room. So I'm left with 134 equals 2 pi over 3 times r squared. I'm going to divide both sides. Let's make things a little easier. 2 pi over 3, I'm going to get that decimal. That's about 2.1. Let's divide both sides by 2.1. 134 divided by 2.1 is about 64. Then I can take the square root. You would get plus or minus 8, but you wouldn't have negative 8 as a radius. So it's just positive 8. Okay. Let's look at 17. Windshield wiper arm to the left is 32 inches long. So this whole thing is 32. If the wiper sweeps through at an angle of 125, find the area swept by the blade. So the blade is right here. So what I see is I see a big circle and I see a little circle. And I want that red piece. I want the area that this red piece has. So I need to do the area of the big circle minus the area of the small circle. So big circle, 1/2 theta r squared. So 1/2, 125, let's turn that into radians. So 125 times pi over 180, which would give me 25 pi over 36. So 25 pi over 36 times r. So the big circle, that would be 32. So then let's see, if I put that all in a calculator, 1/2 times 25 pi over 36 times 32 squared, I get 1117. Then I need to subtract the area of the small circle here. So I know the whole thing is 32 and the chunk here is 21. So the difference for this little r here is going to be 11. So 1/2 theta, same angle, so the 25 pi over 36, but my radius is now 11. So let's see, if I plug that in the calculator, I get 132. So 1117 minus 132 is 985, and that's in inches squared. Right? Last section here, circular motion. So arc length can be used to analyze circular motion. So suppose an object moves along a circular path S with radius r. We have a linear speed and an angular speed. So the rate at which the object moves along the path is called the linear speed, and that formula is v equals s over t, which is arc length over time. The angular speed is the rate at which the central angle is changing along that path. So we use theta over t, which is the central angle over time. Okay, so let's look at these. So a bicycle tire with a radius of 14 inches rotates at a rate of 125 revolutions per minute. Find the linear speed in inches per minute. So V equals S over T. S is the arc length, so r theta, or theta r, and we get one rotation is 2 pi. The radius is 14, and we're doing 125 revolutions. So our distance is going to be 3,500 pi. 3,500 pi. The time is in 1 minute. So if I get the decimal for that, I get about 10,995.6 inches per minute. Let's look at the angular speed. So find the angular speed. So theta is going to be the 125 revolutions, so times 2 pi. So that's going to give me 250 pi. So our angular speed is the central angle change over time, which is 1 minute, to give me about 785.4. Is in radians per minute. All right. Let's do another one. A CD with I'm gonna draw that. CD, the diameter of 120 millimeters, rotates at 45 revolutions per minute. Find the linear speed. So that's S over T. So S is the theta R. So we get, we're doing 2 pi's the 1 revolution, but I have 45 of them. And we want to do the radius. The diameter is 120, so the radius is 60. So that gives me 5,400 pi. And then to divide it by the time is just 1 minute. So that's about 16,964.6 millimeters per minute. Angular speed, it's theta over time. And our theta, we're going 2 pi for 1 revolution, but we're going 45. So that just gives me 90 pi. So 90 pi per minute, which is about 282.7 radians per minute. Okay, let's look at this one. 16-inch diameter, so radius is 8, on a tire makes 500 revolutions per minute. Find the linear speed in miles per hour. Ooh, this is a good one. So linear speed is S over T, and S is theta R. So we get, let's see, 2 pi, radius is that, and we are doing it 500 times. So I get that is 8,000 pi inches per minute. We want miles per hour. So I'm going to write this up here. Inches per hour. I need to convert. Oh, that's definitely supposed to be for minute. My end goal is to get in miles per hour. So I need to convert things. So there are 60 minutes in 1 hour. So that covers my hour conversion. Now I need to get from inches to miles. So 12 inches are in 1 foot. And there are 5,280 feet in 1 mile. So look at all my conversions. So the minutes are going to cancel out. Inches are going to cancel out. Feet are going to cancel out. So I'm left with 8,000 pi times 60 over 12 times 5,280. I'm just going to do that in a calculator. I get about 23.8 miles per hour. All right, let's look at a few more. Actually, we'll do this one and then I'll do the last section. So a circular saw blade with a diameter of 9 rotates at 2,800 revolutions per minute. Find the angular speed in radians per second. So our theta is 2 pi, and we're going 2,800 times, so 5,600 pi radians. And then our angular is the 5,600 pi radians, and that's in 1 minute. I need to convert that into seconds. So 5,600 pi radians per minute, and my end, so I want it to be in seconds. So there are 60 seconds in 1 minute. My minute will cancel out, and I can do 5,600 pi divided by 60 to get about 299. Oh, I do not get that. I get 293.2 radians per second. Right. Alright, we can use angular speed to find the linear speed. Right? So the linear speed formula, remember, is that arc length over time. I can substitute the formula for arc length, so that's theta times r. What if I had to regroup this and make that r times angle over time? Well, that theta over time is that angular speed, so that's just r times that angular speed. All right. So a ceiling fan, the 25-inch blades rotates at 40 revolutions per minute. Find the linear speed of the tips of the blade in feet per second. So W is going to be 2 pi times the 40 revolutions. So I get 80 pi radians per minute. And then my new formula is V equals radius times angular speed. So the radius is 25. And we just found the angular to be 80 pi. So we get 2,000 pi inches per minute. But we want feet per second. So 2,000 pi inches per minute. Let's do feet first. So there's 12 inches in 1 foot. So that covers my inches. And then there in 1 minute, there's 60 seconds. So that covers my minutes. So I get 2,000 pi divided by 12 times 60 to get my seconds. And that is about 8.7 feet per second. And there we have it.